this is a really interesting tool. You're not going to see this second year, third year, maybe, kind of, sort of, depending on the course. So this is just a taste, an introduction to it. So let's not get carried away here. He used to do fancier versions. I won't do those, but I'm going to give you the first go on this. So when you can imagine, as we've already shown, there's cases of specialized constraints, of specialized selections and arrangement problems, and it may well include repetition. And that can get to be really interesting, really complicated. And we might be modeling this in class with choosing cards and so many balls out of a bag and all that. And those things, that's kind of dumb. But like I said a minute ago, you start modeling the distribution of the virus, or how the virus actually infects people. How many viruses do you need to have in you before you get sick? How does that affect based on where they are in your body? How about your general health beforehand? And then those other factors, race, age, and so forth. Did you smoke before? And so forth. All those factors. And you can start looking at things, the closest of people living together. And this is what they've been talking about, these models. And they're doing, and that's what the statisticians, the smart people are doing. Doug Ford, who actually earned some respect from, who I thought was going to be a terrorist version of Donald Trump for a while, has actually listened to the smart people. Bless his heart for that. He saved a lot of lives. And they were really fighting the second wave. I'm not surprised. The second wave in 1919 was way worse than the first wave. It killed a lot of people. This one's a little different, but we'll see. So, and again, it has a broad spectrum of opportunities, which means it's interesting and very useful. It's not a highly specialized tool. So, in this particular general case here, if a sub r, which is just a coefficient, it's sort of like the coefficient of the term. And when we did these squares, we fitted coefficients, if you recall. So that's really what we're doing here. And this allows us, but interpreting this polynomial, this is just something you've been doing. This is just binomial theorem. I mean, you've done it, right? But the point is, it's interpreting what it's trying to say in this context. That's what makes it fun. So if we're going to select our objects in a given situation, then g of x is a generating function for these coefficients, and getting the coefficients is part of what we need to do here. So if the polynomial expansion for our generating function in this case is this one, we can use the basic binomial theorem expansion here. If this is the generating function, this is just another way to write the choose notation, okay, or NCR. It's all the same. So let's just write that. So we can have C NR equals N choose R equals NCR. These are all the same. You know, the same thing. So depending on where you are, your travels, or on your calculator buttons, I think a lot of the calculators use this notation here because it's concise. It's easier to put into a line, and that's often why these. Remember, it's been around a while. So how did we used to do stuff on paper? Typewriters. They don't do well with raised fonts. Okay, so you should go back and look and see how they did vector calculus, like curls and divs and grads and all this kind of stuff. The notation there, it's impossible to read the shit. It looks like runes by the time we finish. Okay. So let's take a look at so consider 1 plus x cubed now in the expansion, because it's a cube, it's 1 plus x times 1 plus x times 1 plus x, right? So when we look at something, a term, we have to choose one out of each of these. And so what we know, and we'll just do this, write ourselves out here, we have 3, sorry, this is the cube version. So it's 464, I think.
131.
1331? Okay. So that's right. So it's 1x cubed, 3x squared, plus 3x plus 1. Okay. Now, to get the 1, we have 1, 1, 1. Okay? It's the only way you can do it. And how many ways? So we're going to have, in this case here, to get the x squared, you could have, or actually he's expanding it the other way. It doesn't really matter. But let me do it. They just did it. He did it as a Taylor series. So let me rewrite it. It's the same thing. You just do it the opposite direction. So 1 plus 3x plus 3x squared plus x cubed. Okay. So here we have 1, 1, and 1. Here we're going to have a number of cases. We can have 1, 1x. We could have 1x1. We could have x1, 1. These are 1s. And I'll go back and show you what I mean by this. So to generate an x, we need to choose, we have to pick 1 from this, and this is x to the 0 plus x to the 1, right? So we're going to choose to make an x. If we choose the x from this one, then we have to choose 1s from these two, right? So that's what I said here. I said, okay, so I'm choosing the x from the far one here, then these both are 1s. That's one way of doing it. I can do 1x1, where the x comes out of the middle guy, or I can do x1, 1, where the x comes out of this one, and these are 2 1s. So there's 3 different ways I can fabricate an x. Make sense? And then that's, I'll do this third term here. Now we need x squared. We need 2 x's and a 1, right? So we can have x, x1. And he was using probably 1 more pluses. Oh yeah, I should use 2. Okay, yeah. We have x1x, and we have 1xx. Once again, there are 3 ways to do it, right? Now I know that you've always multiplied this out just using distributive law, but if we look at this a different way, just the point of this. You have these 3 terms, and you have choices out of each one of them as to how to fabricate the term of interest. And finally, we want x cubed, we have no choice, it's just going to be x, x, x. Notice the coefficients. The coefficients here are equal to the number of choices you have. See that? Now he'll say 3 ways to arrange these choices. And we agree. Picking out of each one of these, that's all pretty flat-footed there. And there's a multiplicity here. We have 2 x's. We have 2 1s. So what we end up with is the coefficient a sub r is going to equal to the number of choices divided by the multiplicity. And this is factorial, factorial. So this would be equal to 3 factorial, because you have already this. There's 3 factorial ways to rearrange 6 things, or 3 things, pardon me. Then you have the multiplicity, and then the First case, there's just one. Okay? And there's only one. So this is 1 factorial over 1 factorial. But let's take the center case, which is more interesting. Here, you either have in this case, we have a multiplicity of the 1's, but we have 1x. So it would be 3 factorial times 2 factorial, 1 factorial. This is the multiplicity of 2 factorial, oh sorry, that's what I meant to say, of the 1's. And this is the multiplicity of x, and this is for the x. And so that's equal to 6 divided by 2, which is equal to 3, which is the collective. Now, the idea of just counting them and getting 3 is just plain luck. All right, so it would be more involved if you went to a higher order polynomial, a higher order expansion. Same thing for the x squared term. Here, it's the opposite case. If I was just to draw it like this, it'd be like 1 factorial, 2 factorial. In other words, now the x, so the 1 has a multiplicity of 1, but the x has a multiplicity of 2, because we need 2 x's to make a square. Okay? And you get, once again, we get a 3. Okay, now he wants to, because this is too easy. So now, consider, and this is where, see the point here, of course, is this is fine, but you don't need it, right? You just choose, you don't need it. So you want to get to something where ultimately it's harder, where this thing gives you solutions that are fairly easy. So let's take one like this. We're going to have 1 plus x squared. Yes?
What is the goal of function? What does this achieve? Like another way
So what we're suggesting here, and it's a little bit of a challenge, because we're just dealing with these classroom pandemic examples, and it's hard to extrapolate that into the real world, and we'll try to do a bit more of that as we move along. But what we're basically saying here, in this expansion, this binomial expansion here, to make these terms here, you're choosing from these different ones and make a combination. Okay? Now, we're just using this example because you all understand polynomials, and we don't have to, we're not talking about the parts of a combine or something where you'd have to have specialized knowledge, right? So that's why we can stick with these things. And I know they're boring, but that's, so we get the pattern, and hopefully, I don't know where he's at in his notes, but we can start looking at where this rolls into things in the real world, where you can use these techniques. And as I show you here, you have less, most of you would be a little ham-fisted in how to expand this. Okay, this is not something you've done a lot of. I didn't do the multinomial theorem in the previous section. We didn't do much with it anyway, but so let me show you how we apply it for this one. So we have, this is to the 4th power, so we're going to have 4 choices. I'll use his notation. So we've got 1x squared, 4 times. Okay? So just so that people aren't confused later. And that's just because it's to the 4th power. There's nothing here that is that complicated. Now, let's see. With the example, I just want to see what it pulls from here. Yes. Okay, so now what the generating functions do is they solve for all the possibilities all at once. Okay? And they just pull whatever out of there. You can't just fabricate that term. Okay? But let's look at, say, one of how many terms In other words, the coefficient. Of x to the 5th. Okay? And so what we can look at here, we say, well, how do we make x to the 5? Now, we only can pick these 3 options from each of them. We have to choose one from each. That's one of the counting principles. So what we could have is, we could have x squared, comma, x squared, comma, x, comma, 1. We have that one.
There's too many options.
And we could have, or, we could have x squared, x, x, and x. And those are the only 2 ways to do it. So these are exclusive. Whatever's going on in one doesn't happen in the other one. So when we finish it, we'll add them. So we'll just put here that these are exclusive. So, in the first one we have, well, we have a multiplicity of x squared and everything else is single, okay? So we're going to have 4 factorial divided by 2 factorial is equal to 12. 24 divided by 2, right? And on the right side, we have a different case. We have 4 factorial yet again, divided by 1 factorial, 3 factorial is equal to 4. So then we have 16 x to the 5th. 16 ways to create x to the 5th. That term. Now we're calling it x to the 5th. It is something else. You could have, you know, these could be genetic strands. And you add and multiply these different strands to make something new. And there'd be 16 different strains, for example, depending on how they combine. And when you have the expertise, you'll know that, as an example. It doesn't have to be polynomials. This is the thing we have to remember, that the patterns we're using here are way bigger than just the examples you're being given. How we doing here? Make sense? Okay.
It's how many ways can you choose 2 2s, a 1 and a 1, right?
Yeah, but think about it. You have 4 factorial total, right? Divided by 2 factorial for the 2 squared.
So in this particular case, I was asking you to determine how many, what the coefficient will be of x to the 5th is in the expansion of this. Okay, now you don't have the multinomial theorem would say the following. So just keep your seatbelt fastened for a second here. You would have something like this.
Like, you have to tell me.
And then you'd have to look at the combinations of A, B, and C that will produce 5. So you're going to say, so that's going to be a sum of 4 factorial divided by A factorial, B factorial, C factorial, where 0 is less than A plus B plus C, which is less than or equal to 4. And this is x to the B plus 2C. And then you've got a table, and before, you know, and lots of work. Because there's more to it, and I'm not going to bore you with it. Look at what we did here. And it wasn't even hard. There's no choose notation. B is a factorial. And that was only there because of definition. We took this apart in the way that you would never think of doing. Yes, sir?
I'm just wondering if this is a fair way to think about this problem, where you're asking, like, let's suppose for the x squared, x1 case, are you basically, like, the fraction, or basically how many ways and you pick 2 powers of 2, 1 power of 1, and a number 1, right?
Whatever you
That's
got to, yeah, to get it to equal 5.
Yeah.
So the max, you're summing your exponents, which is what you do with this. That's what this is. It's just more ham-fisted. Yes, sir.
Is there a more systematic way to find, so here we should x squared, x squared, x 1, x squared, x squared, x squared, x 2.
Probably there is, because when you have 27 terms here,
Yeah.
it's going to get interesting, right? And that's for university.
Of
Okay?
course.
We'll do what we can here to give you a taste of this, just like I did in the physics. And you sit the second year in your algebra back, and you put your hand splitzer, isn't that a generating function? How the hell do you know that? I can remember in an optimization course, we were writing code to do calculus and stuff, and solve differential equations. And he said, so what do we call the number that's left over when between what we calculated and what we should get? And I said, the residual. And I just, and he just stood there, looked at me. And it's like, WTF, how do you know that?
So serious.
And that means there's respect there. There's respect for the student. Because remember, the professor is an expert. He's a world-class expert in this field, or she, pardon me. And so here you are, your voice has barely changed, and you're coming up with words you're not supposed to know. And that just shows their respect for you putting down the video game and learning something that really matters, even if my family doesn't think this matters. Yep,
What in this process is the actual generating function?
G of X.
So, but like in that.
So this whole thing is the generating function.
Oh, okay.
Okay, and so what we're doing is how do we go have a look at it without killing ourselves? Okay, that would be the short way to look at this. So you already see, even if something is involved, and I didn't do it, this would be another 2 columns before we're finished. A monomial theorem, which is supposed to be like the way to do it, okay? Because we had binomial theorem, and we were all very happy and proud of ourselves doing this. But you see as well, and so when you get, this isn't as hard, and this, it does take a little bit of paperwork. So when you're at the simple level, it's like, I'm just going to stick to what I know. Touch not the unclean thing, you see. But now you start getting into interesting stuff. We don't have a theory other than this, which we never learned, before we used to this. And now it starts looking really good. So now, yes, you're right. If we get too many terms here, it gets interesting. And there would have to be more to it. Now, and he may well have done that to some extent with the students, but he's the expert. Anyhow, it's just kind of cool. Let's see what else we got here. Yes, sir.
Yeah, sorry, could you just
Not at all.
explain how you got the 2 factorial, the 1 factorial, 3
Yes.
factorial?
And thanks for asking, because sometimes we have to say it a couple times. It's not hard, it's new. And it's a different symbolism, it's a different kind of thinking. It's writing partly with the other hand. And that's why you have to stare at it and try to suppress the internal resistance you have to change, which is partly what I went on too long, but what I was trying to say before. So here we go. We can reorder this 4 factorial ways. So that's the number of possible orientations. Underneath here is the multiplicity of a given arrangement. Here we have a multiplicity of x squareds. These are singles, they're 1 factorials. There's only one of them. Here there's 2. So the multiplicity, as we call it, is the 2 factorial. Over here you see we have 3 x's. So we represent the multiplicity of the x by the factor. You see? That divides it out and allows us to know how many terms we have. And most importantly here, and we'll come back to this in other parts of the course, these are exclusive. You have to know in your head that whatever's going on in the left's arrangement here is not happening in this arrangement. These are different ideas. Therefore you add them. Okay, you get 16. There's not a union, they're 2 distinct sets. Okay? And sometimes you have to think about what you're doing to know that versus not knowing it. Yes, Steve?
Could you explain the part on the right? Yeah, right.
So this is this. If we look at here, we would have to use the notation of the other board, right? Now, we want to produce a term that has only 1 in it. You only can choose 3 ones. There's only one way to do it, right? Now we want to choose a term that has an x in it. Well, we could have an x and two ones. We can have one x and a 1. We can have 1, 1, and an x. There's 3 ways to do it, modeled here, okay? And so on. And so then you look at your terms, and you say, as I did here, the number of possible terms is 3 factorial, because we have 3, the exponent is 3, okay? But the multiplicity underneath, in the case of the center 2 terms, either case, we have 2 1s, so there's a 2, or we have 2 x's, whichever way you want to do it, okay? So we saw it with Pascal's triangle, which is just interesting. We saw it with choose notation, and now you see it again with this one. And like I said, when we first introduced it to you with the bottom expansion, moving to this over this, I don't know, that's hard to sell. And that's where the danger comes in, because you're going to go, well, I don't want, he's talking shit here, I want to look at this, I understand it, you know. And that's just great, until we move to this board. And then suddenly you don't have anything anymore. This little puppy doesn't work. And you're disappointed. But because you refused, this is not me being mean. This is me being honest. You have a mental block to something new, which some of you do, some of you don't. Depends on what it is. If it's a subject you love, you can't wait to suck up more stuff. Oh, did you see that dude? Whatever. Yeah, sure. Okay. If you're a car guy and you go to the auto show, you're totally open. Oh, you see that dude? You know what? Can't wait for new stuff. If you're a science guy or girl, I shouldn't say that, a science person, okay? And I mean that, I'm not just trying to be politically correct, I really believe that. And you like to figure stuff out and use math as an engine, then new stuff is a pain in the fanny, because you've got to change. And that slows you down for the stuff you really care about. If your video game's working just super duper in Windows 10, then they bring along Windows 11. The nerve. Okay, because there's days go by where you haven't killed an alien. Yours being overrun. Because you're figuring out the nuances, and as we all know, now your mouse won't work, and you'll have to get a new joystick because it's a new operating system, and then this has to get a new patch, and Henry understands. So when you guys write the new operating system, think of me. Alright? Alright. So, here we are. Now let's move ahead. Somebody's been looking for real life examples. Let's see if we can't help her out. Okay, yes sir.
So the reason the actual because you see like addition sums into right?
Yes, so we have three terms here, because this is x to the 4th over 4. Okay? And the counting principle says you've got to pick one from each set. You can't just choose 2. You got to pick them all. Okay? And so that's the same thing that happens here. So these guys here is what's in the parenthesis. Or if you were dealing with non-polynomial stuff, you have to kind of figure out what the parenthesis looks like, as we're going to try and do here in a minute. We're going back to picking up marbles out of a bag, everyone's favorite probability question. And that's it. And the rest is just fabricating and being honest with the counting principle. It's pretty straightforward, actually. And this sounds like a good way to have a quiz next time or something, you know? So, all right. So let's do a little more here. So this is race. Oh.
I'm still a little confused about the multiplicity.
All right, so how many, in this particular case here, and this one here, how many ones are in each of the terms?
I have like
2. That's a multiplicity. If you have 2. How many x's are in there? 1. That's a multiplicity of 1. We don't count that. There's 1 factorial more, right? It's trying.
But why do you pick that specific one? Why not, like,
Well, the one is counted as one factor.
Hang on, shh. One at a time, because if she's curious, half of you are too. So we're trying to create this function. And we would normally not do the whole generating function, because it gets kind of big, right? But we're doing it here because it's easy. So in this case, we're trying to create this term. How do you get an x? Well, you take an x from here and 2 1s. You take 1x1 from 1 1x, right? That's the 3 ways. It's the only way you can do it. And that's what you got here. So there's 3 ways to do it. If you add them up, you get a 3. So that's the coefficient. There are 3 ways of doing it. Now that's just lucky here. Okay? That's what we have to be careful of. It's better in this case because it really is, the total number of opportunities is 3 factorial in the way we can rearrange ones and x's, okay? And then we divide by any case where we're using more than one, which is called multiplicity. All right, and that's true in the x term and in the x squared term. In this case, we have multiplicity of 1. Here we have multiplicity of x, because there's 2 x's. We move over to this example. Here we have multiplicity of x squareds. So we divide by 2 factorial to represent that. Here we have multiplicity of x's. So we divide by 3 factorial to represent that. But we only divide by 1 factorial to represent the single. And I would normally not even write that. I'm just doing it so that you see the pattern. Makes sense?
So the constant doesn't have anything.
The constant, yes. Well, yeah, exactly. So what you told me, I'm sorry, quite correctly, it would be 1 factorial, 1 factorial. Because there's 1x and 1 constant. Or 1x. Okay? And this is where the questions are great if you bold them, so that everybody understands when it's first presented. Okay, let's see if we can get this marble thing done first, before we do something else. So we have a bag of 3 green, which we'll call capital G, 3 white, called capital W, 3 blue, capital B, and 3 red, capital R, just so we don't write the colors every time. We will select R of these. And I'll do it over here. So these terms, we're going to call them E1, E2, E3, and E4. And so we said this one here is going to be x to the r. So this implies that r equals 5. So if that's true, then we have E1 plus E2 plus E3 plus E4 equals 5.
Oh, yeah.
Okay? This is just the count of how many of each of these we have. Okay, so we chose the second exponent here. So this is 2, 2, 1, 0, for example. Here it's 2, 1, 1, 1, 1. But no matter what we do, so this is the exponent. In this example, here the exponent. So what I mean to say, yes, of the term member, of the selected member. Okay? So, now we don't have polynomial anymore, we've got something different. But here's what we know. E1 plus E2 plus E3 plus E4 is equal to R, and there's a limit. 0 is less than e to the EI, which is less than 3. Why? Because we have 3 balls. Now later on I'm going to show you an example, whether I get to it today or not, where it's different numbers for each one, like there's different cases, it gets more complicated. And this makes this structure, this organizing concept, so much more powerful. Yeah.
So when you have it here, it's not an exponent, it's just the number of them.
Well, yes, it's the number that we're choosing. Let's let this roll out a little bit, okay? And so this is, we're going to do these, in this case, E, G plus EW plus EB plus E big R equals small r. So it's clear. Okay? And this is the number of each chosen. We can convert this to, based on how we interpreted things over here, g of x would equal x to the 0 plus x to the 1 plus x squared plus x cubed to the 4th power. Now let's understand why. These are the choices. 0 to 3 false for each color. Now we're not distinguishing color here. This is just one, and since they're all the same, it's easy, right? There's 3 of each. So we don't have to distinguish. Otherwise, you'd have to have more than one term. But we don't have to do that here. So, and then we have 4 different colors of balls. Now, I know this just looks like a polynomial, and you can see, no matter whether it's physics or math, see how we're using this mathematical construct to interpret a real-life problem.
So the number of terms inside, I guess, can always be equal to x, so not choice is the same.
It's the number of choices plus 1, because you have to do the 0. You have a choice, you can choose any.
Okay.
Okay? But you still have to make that choice. And that was what we were doing over here. When we did the 1s, we were choosing no x's. Okay? It looks like we're choosing a 1, but we're fooling ourselves. We're choosing no x's. So we had, in this example here, you were choosing either a 0 or a 1. Here, you were choosing a 0, 1, or a 2. Okay, and so on. Okay. All right. So now, there's all the stuff using those wipes and I can use the board cleaner. It's not working as well. Okay, we'll figure it out. So, now he stops with this example just by showing you how you obtain the generate function. Okay? But let's extend it slightly and say we want R equal, because we're doing okay here. We can choose whatever we want. And we know these could be 0. We can choose R is equal to 0, right? We just want to be kind of boring, right? And it could be as much as 12. So let's choose, well, we had 5 before. That seems like a nice number. Why don't we make it 5 again, just for fun, okay? So how many ways, this is a little bit more difficult, to produce R equals 5. So let's see here. We have so we've got these. I'm just gonna do 1 here, and we know that we've got 4 of them. So we've got x to the 0, x1, x2, and x cubed. So if we want to produce equals 5, we could have x cubed, x squared, 1, 1. That would be one way to do it. We could have x squared, x cubed, 1, 1. And we're going to have quite a few here, right? Because it's basically going to be yes, sir.
With the x squared x cubed, what would be the same as
Yeah, x squared doesn't matter.
We're choosing, let's see now, would that be the same? That's an interesting question. I don't think so. It's a different option. The same way we had here, you had 1, 1x, x, 1x, sorry, you know what I mean? Like there's different orientations, they all matter. So this can take a while. So let's see, because we also could do x squared, x, 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 but that's a one-off, but we can move that around. Okay, now as you say, do we have, but we would have a lot of choices here. Okay, because we could do x, x, x squared, x, and so on. So, well, I can't finish this, I probably bit off more than I can chew here. But, because there's a whole pile of ways to do this. Yes, ma'am?
So like each position is a different color? So
That's
the
right,
first one is-
yes. They are, that's right. So each one's a color. So we could have, in this particular example,
So it's like-
green, white, blue, red.
So it's like 3 green.
That's right, exactly, yep.
How do we have 2 ones? So we know, I know we have the x and 0, which is
That's all they are. Because we need the exponents to, one at a time. We need the exponents to sum to 0, or so, to sum to 5. So 2 plus 3 is 5, plus 0 plus 0. Come with the exponents of x here. And that's how you get a 1, is x to the 0. So maybe to be fair to you, I could write x to the 0, x to the 0. That's what I mean.
how do we have 2x to the 0 so we don't have that set?
No, we have, yes, but we have 4 sets. You take, so you're taking something from each set. Not, you can't take more than one from one set, but you're taking from different, it just happens that each set is identical. Now, there'll be examples, probably not today, where we have different size sets, and that's more complicated.
Okay, but what you're effectively saying is you take 3 of one type of marble and 2 of another type of marble. And if you take all the ways you can take that, you would include the second one as well. It's like the first 2 would be the same way as on the right side, we don't have separate cases for like x squared x, x squared 1 versus x squared x squared x 1.
In this case, I should just suggesting, so we can't, okay, all right. Okay, if that's, okay, fair enough. Okay, let's go that direction,
Because I think
which would be making it a lot easier, because we don't have to, that's a good thing. So we can have, okay, so let's go that direction, because I see the pattern. I was looking at it another way, but now I see what he means. Because before, when we did it, we actually mapped them out. Now we're not worried about that anymore. So they're talking about the general concept here. So we could also do x squared, x, 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 right? And that's about it. Is there any other way to do it? Yeah.
hold on. There'd be x cubed, x squared, 1, 1, x cubed, x to 1, x to 1, 1.
Right,
I have
okay.
4, I think.
Okay, good. I agree with you here. So we've got x cubed, x, x,
1.
1.
X squared, 1, x squared, x, 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 x squared, x squared, x, 1.
There you go, there's your 4. Okay, now these are exclusive as well. Whatever's going on with one version doesn't affect the other versions. So what would happen now is we'd say, okay, well, we have 4 factorial, because this is the 4th power, divided by 2 factorial, plus 4 factorial divided by 3 factorial, plus 4 factorial divided by 2 factorial, plus 4 factorial divided by 2 factorial. Now, again, they're exclusive, so you can just add them up. All right, so this is going to be 24 divided by 2, 12,
12
plus 12, plus 12, plus, and then 24 divided by 3, or 6 or 8 is 4. So then we have 36 plus 4 is equal to 40.
56 factorial.
And this would be 40 ways, pardon me, to pull 5. by
It's like a backwards pie.
I factored out the trial handed out.
Why don't you use a big calculator? Just go in your head, bro.
I like my
Okay.
calculator.
So I think it's time to have a quiz. Now we have a different question. We're going to show you how we start using constraints on how we distribute things and the power of that. So in this particular case, we want a generating function. We have our identical objects, but we're going to put them in different boxes. But now it's going to be different. So we have 5 boxes. Right? And the first 2 can be less or equal to 10, 3 to 5, 3 to 5, 3 to 5. And this one, these first 2 have to be even. So we have E1 plus E2 plus E3 plus E4 plus E5 equal R. 0 is less than or equal to E1 and E2, which is less than or equal to 10. And the second condition is 3 is less than or equal to E3, comma, E4, comma, E5, less than or equal to 5. Now that's not so hard to pull from the question. Now, so here you're going to have 0, 2, 4, 6, 8, and 10. 0, 2, 4, 6, 8, and 10. 3, 4, and 5. Right. So, once again, we're going to have one distribution here, which is going to be x to the 0. Plus x squared, plus x to the 4th, plus x to the 6th, plus x to the 8th, plus x to the 10th, squared, times x cubed, plus x to the 4th, plus x to the 5th, cubed. That's your generating function. And then when he asks you that, that's all you have to do. Then we can take that ultimately and look at generating, because what you want is the coefficients, right? Because you want to know how many. If we choose R to be, whatever, 16 or something, how do you do that? What's the combinations that make it work? Okay? And so we start looking at that, and of course when it gets bigger, like we talked a few minutes ago, that does get more complicated. Mercifully, we don't have to deal with every conceivable case. So you could play around with, since we've been doing this, let's make R equal to, well, I said 16. That should work here, okay, because 3 times, we have to have, this has to be at least equal to 9, right? So R would be, 9 would be greater than or equal to R. And then the maximum on the other side would be, what, 25? I guess, we max it out.
35. 35. Because 10, 10.
Oh yeah, I just can't add. Thank you. That makes, I'm relieved. I thought, what am I not getting here? It's just addition, so there's the only choice. We'll choose 16. And so then we can look at this. And this might keep you busy for a few minutes, but it's good for you. Okay? Because you're going to look at, you've got 2 separate situations. Okay? And so I'll let you stare at that a little bit, because that's a pretty cool question. Okay, now the coefficients, these next 8, we're not going to do that until, well, tomorrow I'll go back over this stuff.
So, Thursday.
And so that would be Thursday. Now, 1 second. I'll give you another one to think about. a generating function. I'm just going to use g of x to save writing to model counting all selections of 6 numbers six objects. That's it. Chosen from 3 types. With a repetition of up to 4 objects from each type.
Oh.
And you can put this together based on what we've been doing, okay? So when I did this before, I said to you the exponent meant something, and then the options meant something. I think I did with the ball, with the green and yellow colored balls, I forget now. So you have to remind yourself, because it's so easy just to think of it as an algebraic expression. So maybe what I would say to you then also is, so in g of x equals, I don't know, x to the 0 plus x squared plus x cubed to the 5th. What does this represent?
That's wrong. He's just giving an example.
Oh.
Just giving an example. Just,
That's,
it's wrong.
okay, and
Without it.
what does that mean? Okay, so it's just an exponent anymore. It means something. You need to make a page or part of a page and lay it down and draw it out and put arrows pointing to everything and tell you what it is so you get confused, go back to it again. Because I'll tell you folks, in this business, definitions, definitions, definitions. And with that I would add the context, which is what we're talking about here. You know that's an exponent, that's the easy part. Okay, and so how do we do this, right? So this would be 0 to 3, 5 times, right? There are 5 different choices. So this might be an example of taking 5 balls of 3 different colors, or 4 different colors, 3 different colors, whatever, and so on. However, yeah, these would be the colors, and that would be the number of balls you're drawing. That's an example. You need to spend time getting your hands dirty on that, and that's important. Why you want to go back over this and convince yourself you understand what's going on, and that's why I suggest you take that on too. There's a couple things to do. Okay, we will not have a test next day.